Okay, hi everyone. Just thought I'd go ahead and get things started here a little bit. Go ahead and say hi if you're hearing me and everything like that. I see there's already a question from Chase up in the stream chat, so feel free to continue to ask questions as we go along here. So I think what I'll start out by doing, and I'll get to Chase's question here in just a second, is just to give you a little bit of an overview of that first set of lecture notes. To give you a little bit more of an idea, a little bit more, I guess, background on how things work with regard. Hey, Sammy, hi, Zach. The other thing that I'll note here is that there's about a 10 or 15 second lag between what I do and then when you will see it on the screen. So there's going to be that little bit of lag. So sometimes I'm going to pause for questions for 15 or 20 seconds or something like that, just to see if you do have questions. But note, I'm not ignoring you or anything like that. There's just a little bit of a delay between when I do something and when it goes up on the stream. And the reason for that is that it's actually making the video as we speak right now, which is kind of cool, because what it means is as soon as this live stream is done, it's going to be available already on YouTube for you to watch again and review and stuff like that. So I think that's useful to do, and that's why I'm using live stream instead of maybe Zoom or something like that. So hopefully that works. If you think it's a little bit too clunky or something like that, please let me know in the discussion boards on the D2L website, and we'll get it fixed, and we'll look into some other methods or something like that. But I've used it now for 2 of my other classes, and it seemed like it worked okay, and hopefully it'll work okay with this group too. But if not, like I said, just let me know, and we'll fix it and make it better in some way or other. Like I said, the first thing I'm going to do here before I start taking questions is give you a little bit of background on this idea as we are moving forward with where we were at before we had a break for spring break, which turned out to be a little longer than we thought it would be. So just to remind ourselves where we were there, we finished up talking about Gauss's law and what Gauss's law means, and the idea of the electric field was something that came before that. And then now we're dealing with that last chapter in the sort of the basics of electricity before we get into practical stuff like circuits. And these basics, the last thing we have to talk about, the basics, is the definition of what is, I guess, technically called the electric potential and the electric potential energy. The more common term for electric potential is actually the voltage. That's the everyday term for that. And the reason for that is because the unit of the electric potential is the volt. So voltage is the difference in the electric potential between 2 spots. So let's talk a little bit about the work done, the electrical potential energy, and then the electric potential, which are 2 distinct things, which seems a little weird, but that's the way it works. So let's go ahead and do that. If you have questions, feel free to just post them in the chat as I'm working here. I'll get to every one of the questions. Chase has already, like I mentioned, already asked a question up there, and I'll get to that one. Hopefully this one will provide this sort of background so you'll know kind of what I'm doing when I answer that one as well. So let's go ahead and dive in. So let's say that we're talking about, I've got a point A, a position. Oops, hold on. We're going to get my brush here. I got a position A, so I'm using my super sophisticated paint program here to kind of give us a little bit of a blackboard or a whiteboard or whatever. So let's say I've got this point A, the spot in space A, and I got another point down here, over here somewhere, and I'm going to label point B. And let's say that I'm going to move a particle, a charged particle, along some wandering weird path. Doesn't have to follow any particular path, but I'm just making this arbitrary one, and it ends up following this path going from point A to point B. And let's say that the particle happens to be charged. Now, if we have an electrically charged particle, as it moves along this path from point A to point B, there's going to be some work done by an electric force that acts on it. So let's talk about the work that's done in going from point A. That's supposed to be an A. Just imagine it's a really good A. And I'm going to point B, and that would be equal to, now the electric force on the charged particle, because the field might be different at these different spots, we're going to have to use the integral here. We got to find out, sort of the area under the curve thing. So remember how you do that. We're going to find the integral. So we're taking the integral, and we're going to go from, I'm just going to label this. I'm going to go from point A to point B. Those are going to be the limits of my integration. And then I have to, the thing that I'm integrating is the force dotted into the differential displacement along the path and displacement. I'm going to call it ds. And then I've got an integral, or sorry, a vector sign over it to indicate. Now ds is just a little tiny little, I'll just, it's like this little kind of little line right here. That, if we imagine there's an arrow there that goes from here to here, that would be the little ds vector. And then I would say, well, what's the electric force along that little vector going from there to there? And if I add up all the contributions to all little ds's going from point A to point B and what the forces were along them, this will give me the total work done by whatever force. Now, if this is an electrical force, if it's the electric force, then we're talking about the work done by the electric field. If it's an electric force, then the force, of course, would be related to the electric field and the charge that is doing the moving. So I would take the charge that's doing the moving, and I would multiply it by whatever electric field there is in this region along this path. And I would say that would be the force that I would put in there. So the work done in going from point A to point B is equal to the integral, and I would have to evaluate this integral at the endpoints here that go from, it starts at point A, goes to point B, and I have Q times the electric field dotted into ds vector. Okay, so something like that. Now here, so that's the amount of work done this in going from point A to point B, using the fact that we've got an electric field here as a charge is doing the moving. Now, this isn't all the work done. This is only the work done by the electric force as it goes from here to here. For instance, I could take a little tweezers and take the charged particle and move it from point A to point B. Of course, I'm maybe exerting a force on the charged particle too during that time, when it's moving along there. But this only calculates how much work the electric force is doing. Okay, so that's that. Now here's the deal. We know for conservative forces that the work done by a conservative force can be associated with a change in the potential energy of the force, just like with gravity. So if I have my calculator here or something like that, I've got my calculator and I say, well, if I move the calculator from this spot right here to this spot over here, gravity did some work while I did that move, and of course there was a change in potential energy as well as it moved from point A to point B. The same thing is going to be true for the electric force. But notice that the general expression for how the work done by a force and the change in the potential energy associated with that force always works like this. It says that if you have work done in going from point A to point B, then that is equal to minus the change in potential energy in going from point A to point B. It's always minus. So for instance, if the work done by gravity as I go, say, from up here to down here, the work done by gravity is positive, but notice how the potential energy decreased. Now the reason that the work is positive as it goes from here to here is because the gravitational force is down, and the displacement vector for all the little spots along here along the path was also down, so the work done, this dot product would be positive, and I'd get a positive amount of work done. But notice that corresponds to a decrease in the potential energy, so there's a negative change. That's why there's that minus sign there. Because if the work done is negative, the change in potential energy is positive, whereas if the work done is positive, then the change in the potential energy is negative. So there's this inverse relationship just in general. The same, of course, is true for the electric force as well. So then I can look at this and I can say, well, this work done in going from point A to point B I could just say, well, that has to do with the change in the potential energy between point A and point B. So I'm going to sort of infuse the minus sign in here. I'm going to say the change in the potential energy in going from point A to point B, electrical potential energy now, is the minus sign. Notice I just moved to the other side, and this is the expression for the work. is equal to Q times the electric field vector dotted into ds vector. Okay. So there's that. And this basically, this change in the potential energy would be, of course, final minus initial. So that would be, for instance, the potential energy at B minus the electrical potential energy. Both of these are electrical potential energies. The electrical potential energy at A. Now, okay, so that sort of got us to the idea of thinking about electrical potential energy. So when charges are moving around and they're experiencing electric forces, there's a change in potential energy which can be calculated in this way. You can take Q and then, minus Q. You can bring the Q out here because the charge of the moving charge doesn't vary with the position. So you can just move that out. You can say it's minus Q times the integral of E dot ds. So that's the idea of the electrical potential energy. Now, I'm going to take a little bit of I'm going to divide this off a little bit and talk a little bit about something slightly different, but is related to this. Here's the deal. Let's say that you did not know what charge was moving between a point A and point B. There is a charge. Let's say there is a charge moving between point A and point B, but you don't know how much charge it has. Well, I can't know how much potential energy difference there's going to be going between point A and point B because you don't know exactly what the force is, because the more charge it would be, the bigger the force would be. But we can characterize this by a different quantity. That doesn't depend on Q's. To make that explicit, I'm going to define the electric potential, not the electric potential energy, but the electric potential, a function, a quantity whose change is equal to the change in the potential energy divided by the amount of charge that's doing the moving. So this delta V here is the difference in electric potential between point A and point B. And I find this by taking the change in the electric potential energy and dividing by the charge. Notice that now this electric potential does not care what the amount of charge that is moving from point A to point B. Doesn't care what that is. All it cares is, well, what's the electric field like in that region of space between point A and point B? It only cares about the sources. It doesn't care about the recipient of the force. Okay, so this is going to have the units of a volt, and you can see from this expression here that if potential energy has our usual units of work, which is in joules, and Q, the charge, has our usual units of coulombs, that the unit of electric potential would be the joule per coulomb, and that's what the volt means. The volt is a joule per coulomb. Okay, I just saw what Luke said up there. Says, okay, glad to have you along, Luke. But yeah, this will be available to look at later as well. So good luck in thermal. Hope it's fun. Okay, so the change in voltage is equal to the change in potential energy divided by that. And notice that because of this, I can say, well, the change in voltage between any pair of points can be calculated without knowing how much charge is actually moving. It is equal to minus the integral of E dot ds. And I have to integrate between the 2 points in question. Imagine that's a B there. It almost looks like a B. I know it's getting a little full there. Okay, so that's where the definition of the voltage comes from. It comes from the definition of the electrical potential energy, which we use the basic idea of work to define. Okay, so I'm going to pause for questions on this. So I'll wait, 15, 20 seconds here to see if you have any questions on that. If you don't, just say no questions, or it's clear, or it's all good, because otherwise I'm not sure if my answer has gotten through yet. So go ahead and ask questions or say, that looks good, don't need to know any more about that. Then we'll get to Chase's specific question. Okay. All right. So if there aren't any other questions, I'm going to clear this out. So we'll just clear it up. Okay. All right. So good. All right. So let's talk then about Chase had a question. He said before the stream started. He said, "Can you go over the first non-multiple choice example problem on 11.1 slideshow?" Okay. So if I recall right, let me look at that now. It says we have two parallel charged plates of opposite charge density. So the electric field for that is uniform in both magnitude and direction. The value of the electric field is 1.5 times 10 to the 5th newtons per coulomb, and it points away from the top plate. So I'm going to draw this in here. I'm going to say, all right, we got a, oops, I need my brush, not my selector. Okay, so let's say here I have a top plate. Here's a plate, and here's a plate. And I know that in the region between the two plates, this is going to be a little bit awkward, but it has an electric field strength. And let's see, it points away from the top plate. So I'm going to put in the electric field vector here. It's 1.5 times 10 to the 5th. That's a 5. Newtons per coulomb, that's the unit of the electric field. And it points down. So I'm going to say negative j hat for now. So it points down. And that's in the region between the two plates. And the reason I know this is that it says that it points away from the top plate in this region between. So this is the strength of the electric field, and it points downward at this case. Okay. It says, what is the potential difference between these two plates if they are separated by a distance of 1.5 centimeters? So I'll just put this in here, that this distance right here, that separation there, is 1.5 centimeters. I'll probably run out of space here. 1.5 centimeters. Okay. So there's that distance. Okay. So I think that's the question. Now, we're going to use that definition that we just talked about to find the difference in electric potential between the two plates. And we're going to do it this way. We're going to say, all right, let's say the change in the electric potential. And one thing I want to point out about this too, which I didn't make entirely explicit, this is not a vector quantity. This is a scalar quantity. The result of the calculation that we're about to do is that I get a scalar quantity in difference, just a number that has units associated with it. Okay, so the change in the electric potential between any 2 points, A and B, is we just take the electric field, dot it into some infinitesimal displacement vector that is part of the path that I'm using to go from point A to point B. Okay, so this is what we're going to do. I'm going to say we want to know what the difference in potential is between the top plate and the bottom plate. And here's how we're going to do it. I'm going to say this spot right here, this is on the top plate right here. I'm going to call this point A. And I'm going to get to the bottom plate. Now I can go any place on the bottom plate that I like. I'm going to call this place right below that, I'm going to call that point B. Okay, and the reason I'm going to do that is because, in fact, I am free because the electric force is a conservative force. I'm allowed to use any path I like because, remember when we talked about conservative forces back in 1081, one of the rules that we had about it was that if it's a conservative force, the work done by that force should not care about what the details of the path. It only cares about where point A is and where point B is. It doesn't care how you got there. So I can choose any path that's convenient here. That's nice. But that also, and the reason that works here is because if it's a conservative force like the electric force is, the work done is independent of the path, which means the change in potential energy is independent of the path, and which means the voltage difference between the 2 points is also independent of the path. So that gives me complete flexibility to choose whatever path I like. And the reason that's so nice is because I can choose a path that goes straight down. Imagine this is straight. It's a straight line which points exactly from point A to point B, and this is as good as taking any old wandering paths I like. I can, make it as complicated as I like or as simple as I like. I say simple is better. So let's do that. We're going to do simple. Now, what does this path look like? Well, every ds in this path is pointing, I've got to have a sense to it as well. I've got to get from point A to point B. So I'm going to put an arrow here to indicate that I'm traveling exactly downward. Okay. Now, what this means is every point, every little infinitesimal little vector ds that is here has the exact same direction. ds is always pointing straight down. So, in other words, I can rewrite this expression as, all right, there's this intrinsic minus sign. So this is the difference in voltage between B and A. Final minus initial. I'm ending at B, starting at A. So final minus initial, the change in the voltage is equal to minus, okay, the integral of, okay, now we will put in, let's have a look at what this dot product looks like now. E has a magnitude of 1.5 times 10 to the 5th newtons per coulomb. The direction is negative j hat. ds has a magnitude of, well, you just got to say ds. And it also points downward. So ds is like negative ds j hat if I want to put that in there. But I'm going to have a negative j hat dotted into a negative j hat. That gives me a positive number. This electric field, so this electric field has a magnitude, and we've just done the dot product. It has a magnitude which does not change. It's the same. It's uniform. It's the same at every point here. So I'm going to be able to pull out the E. Okay, so we got rid of the dot product because the E and the ds are pointing in the same direction the whole time. And then I can pull the E out of the integral because it's uniform. It's the same strength the whole time. Okay, so what do we get then? We get minus E comes out of the integral, and it becomes the integral of ds. Well, what's the integral of ds? It's just s, which is the path length. That's it. It's just 1.5 centimeters. So this becomes really easy. We got a minus. We got the magnitude of E. Okay, the minus sign here comes from the intrinsic minus sign associated with the formula. And we put in the magnitude of E, which is 1.5 times 10 to the 5th newtons per coulomb. And we multiply that times, when we integrate ds, we just get s, which is the total length of the path, which is 1.5 centimeters. So I'm going to put that in as meters. That's 0.015 meters. Okay, and I ran out of space here, so maybe I can make this a little bigger. Maybe I can make it a little bigger. I'm making it a little bigger because I have skills like that. Okay. So now I just multiply this. I got my calculator, no problem. It's 1.5 times 10 to the 5th times 0.015, and I get 2,250. It's minus 2,250. And I'm going to see the units here. I see newtons times meters, that's a joule, divided by a coulomb. Joule per coulomb has the units of the volt, named after Volta. What's his name? Okay, so what does this mean? Let's interpret this. Why this minus sign? This means that as I go from here to here, the voltage drops by 2,250 volts, which means A is at the higher potential. And as I go from B, it goes to a lower potential. I've decreased the voltage in going from point A to point B. So A is at the higher voltage. B is at 2,250 volts, smaller than A's voltage. And we found then the potential difference, or the voltage between the two spots. Okay. So that was the answer, hopefully, to Chase's question. I'll pause now to see if there are any other questions on that, or if folks have a new question about homework or any of the other lecture notes or anything like that. And again, if you don't have questions, just say we're good or something like that. So it looks okay. I don't see any questions. All right, if not, I'm going to erase this. We can start with some other stuff. Okay. So folks are happy with that? So feel free to chime in with any other questions that you might have about any of the other homeworks or anything like that. Hopefully that was useful. But I could talk a little bit now about how to use this definition of voltage a couple of different ways. So I'll mention that at this stage. So I've got that integral formula that we have there is really good for calculating differences in potential and differences in voltage when you know what the electric field is. So Chase had another question. So I'll finish this point and then I'll get to Chase's question. If you know what the electric field is, it's good to use this formula that the change in voltage between any 2 points is equal to negative integral E dot ds. That's great. But what if you don't know that? What if you know about what the sources are, but you don't know what the field is? So for instance, what if I have a whole bunch of charges and I want to know what voltage those charges produce? Well, what you do there is we start with our basic thing that we started with electric fields, and that is this change in, whoops, sorry, we got to get my brush. The change in the voltage is equal to minus E dot ds. We start from that. And I see some questions are popping up now, so I'll answer those as soon as I get done with this thought. Let's start with a point charge. Point charges are, E dot ds. This is the general expression. If it's a point charge, then I know that the electric field of a point charge, oops, that's a long vector sign, but you get the idea, is kq over r squared r hat. Something like that, where the r hat here points radially away from the charge. Okay. If I plug this in here, I can show that this gives an expression for the voltage for a point charge. Namely, that the point charge produces a voltage which is equal to kq over r plus c. Now, whenever you do if you ever do, is you know this already from your from calculus class. If you do an indefinite integral on here, like we're kind of doing here with this electric field, plugging in here. If you do an indefinite integral, you get a plus c on the end. Okay. Same thing happens here. If you do this indefinite integral, you find out that the voltage due to a single point charge is kq over r plus c. Now, a lot of times we take c to be 0 just to simplify this formula, but you can take c to be whatever is convenient. And that is equivalent to saying you can set your origin wherever you like, and sort of like that with gravitational. So remember, only differences in electric potential matter in the same way that only differences in potential energy matter for gravity, that sort of stuff. So this formula is useful for finding the voltage and the potential difference if you already know what the charges are and you don't necessarily know what the electric field is. So KQ is a good formula for that. So now I'll answer some of the questions that are in here. So first of all, Zach's question, I'll get to Chase's, but Zach's question, is the lab from before spring break due on Friday? I don't have a specific due date on that just because we're not going to be doing labs yet for another couple of weeks. So just to sort of keep in the spirit of what we've been doing throughout the course of the semester, I won't ask you to turn in that lab until the next lab is happening. So we've got a little bit of time here before the next lab. So I would just get ready to turn that in electronically if you could. So if you want to, if you want to type it up and maybe I'm trying to remember which one. Oh yeah, it was the field mapping one. We'll have to have if somebody in your lab group has a scanner, if you could scan it in and I'll have you email it to me or something like that. That's the plan anyway. So if you could sort of get ready to do that over the next week or two to submit it electronically, I think that's probably the way to go. But I'm not going to have labs due until we actually have the next lab, which will be in Tinkercad after we have our next exam. So we have a little bit of time before the lab is going to be due. Chase's question. For the equipotential formula, what are the symbols in front of the V? Slide 3 of 11.2. All right, so let me have a look at the slide that you're talking about. Slide 3 of 11.2. Today's lecture notes. Aha! Oh, okay. All right. Yep. All right. So this is the symbol he's talking about. Okay. So let me get rid of this first. We have a clean slate here. Okay, so this is what he's talking about. I was talking about, or for instance, I had this situation where I have the electric field, the X component of it is equal to negative the dV. This is actually a special D. Okay, it's what we call a partial derivative. Okay, so what this means is the following. So this is like going. This is like going back. What if you know the voltage and you want to figure out what the electric field is from it? Well, if you remember, I mean, where does this sort of come from? It comes from this idea that, remember, the difference in voltage is equal to minus integral E dot ds. Which any ds that you're talking about here could have x, y, and z components, depending on which way you want your little path to travel. Okay, notice here that to undo this, if I wanted to solve for E, if I happen to know V first somehow, if I go back, what do I have to do here? What am I doing? The inverse of the integration operation is differentiation. So the electric field would be delta V over delta S, in a sense. But, there's this dot product involved in there, and there's E as a vector and all that sort of stuff. It turns out that if V depends on the three coordinates, X, Y, and Z, the X component of the electric field would be equal to minus, and that minus sign comes from there, dV dx, where this special symbol for the derivative, this special D that shows up there, is a partial derivative, which basically means, yes, I know V depends on X, Y, and Z, but I want you to regard the Y and the Z dependence as constants and differentiate only with respect to and leave the Y and the Z alone. Similarly, if I was going to say, well, I want to know what the Y component of the electric field is, it's negative dV dy with the partial derivative. So it's saying that partial derivative means leave X and Z alone and differentiate only with respect to Y. So that's why that symbol is a little different. If E only depends on X, then this symbol you could just put a regular D, not the script D in there, because that's what we would call the total derivative, and it doesn't, you don't have to worry about Y and Z even being there if that's the case. So that's the symbol. Hopefully that explains where that comes from. Yeah, it's a crazy looking D. It's the partial derivative. Yeah. Okay, any other questions? I'm pausing just to wait for a couple of questions here, and as I do, I suppose I could give you a little bit more information on things as well, just as we sort of make our way through. And feel free, continue to ask questions here as you need to and as you want stuff to get answered. But the next stage, so then, is you can use this idea that if you know the voltage, you can find the electric field. And sometimes calculating the voltage is easier than calculating the electric field directly from the sources. So, sort of an example, let's say if we have like a blob, a charge, or something like that. I don't know. I shouldn't draw crazy blobs like that. But I've got, sort of a weird blob of charge, and I want to know what's the electric field at that point up there. What you can do is you can say, well, actually, the electric field is a complicated vector formula. Remember when we built our vectors to calculate electric field from continuous charge distributions? We said, oh, let's take a little bit of this charge distribution there. We could say, all right, then there's a vector that points from there up to the field point where I want to, the X marks the spot where I want to know the electric field. Well, here what we can do is we could say, well, I don't care about the vector nature of this. The voltage only cares about how far this spot is from here. Because remember, it's the formula for the voltage due to a single point charge is just a scalar, kq over r. You just need to know what r is and how much q is in that little piece. So that actually it means that, there's a little bit of voltage due to this little charge right here, and I can add up the contributions to to the voltage from all the little charges in this distribution. But I don't have to build the r vector and the r hat. I just need to know what the magnitude of r is. Then once you have the voltage at that particular spot, you can calculate the electric field by taking the derivative with respect to x, y, and z to get all the components. Now, a simplified integral and then having to do a derivative can actually be quite a bit simpler, mechanically speaking, than trying to do that integral where the vectors are involved. So that ends up being useful. It's more steps, but each step is a little bit easier than the one big step that we use to calculate the electric field in the first chapter of this unit. Chase is asking now, will we be able to have Zoom meetings during your office hours? There's a possibility of doing that. I have yet to get into Zoom, but I can look into it if you'd like to have individual meetings. I think there's a lot of mileage in having live streams with a bunch of people, but if you want to have you need some quick one-on-one time or something like that, then it's possible to do Zoom once I look into it. I'll let you know early next week what things are looking at on that front. And I haven't checked my email much this week yet. I'm sorry about that. I've been keeping an eye on the discussion boards and doing these live streams from my other classes and stuff like that. So if I missed an email, I'm going to be checking back later on today and early tomorrow to make sure I didn't miss anything. It's a little bit better to probably use the discussion boards. I'll ask that of folks too. If you could use the discussion boards to ask your questions, that's better, I think, for everyone. And the reason is it lets me answer a question in public that everyone then can see the answer to, rather than answer it once for you and then maybe somebody else has the same question and then I've got to answer it a number of times. So I'd rather, unless it's like a private thing, like you need, you don't want anybody, nobody else in the classroom who needs to know your personal business or something like that, you can use email then and I'll be checking in on it. But other than that, I think it's generally better to have it in the discussion boards that are on D2L so that everybody gets the answers rather than just a few. So I guess I'll open it up for more questions now. The next exam, I am planning on it being mid next week. Maybe I think I'll probably open it up on Wednesday for a couple of days. That is what my plan is. But this chapter is the last chapter before we do that. And it'll cover the chapters on electric force, Coulomb's law, and the idea of the electric field, and then it'll cover Gauss's law, and then it'll cover this idea of electric potential. And I am giving an exam in another one of my classes this week, and they'll sort of be the prototype, and we'll see how these online exams go. But I think it'll be okay. Generally, in case you all haven't had a chance to look on the discussion boards, the general principle is they're going to be online. you're gonna have more time to do them, and I'm gonna compress them a little bit as far as number of questions. So there'll be a couple fewer questions in each sort of section, but still have the same distribution. And Sammy just asked, when is can I go over the third slideshow? So yeah, I can go over that for sure. Let me look at what we're... All right. So that one, there actually wasn't a ton of material in there that was representative of what's necessarily in the book. I talked a little bit about how conductors and potential electrical conductors interact with the idea of voltage and electric fields and that sort of stuff. And then I gave you some applications, some sort of little bit of extra information about how voltage can be used to do all sorts of different things. Like I talked in there about Millikan's oil drop experiment, which was the first time that the electron's charge was isolated and measured. And that was a pretty interesting experiment, but it's pretty tedious. I did it as an undergrad. It's not that fun to actually do, but it's fun to analyze. Then I talked about the Van de Graaff generator, which is basically the first particle accelerator, about how that works. And we talked about the electrostatic precipitator, which is used to scrub smoke and reduce air pollution and stuff like that. And then we talked a little bit about xerography as well, which is basically how a copy machine works. And it uses the idea of a photoconductor to do that. So those are basically just examples of how voltage and charges can be used to do useful things. But let's talk a little bit about the conductors and the electric potential, and hopefully that will be that'll give you a little bit of information about how these things work. So I'm going to erase this so we have a clean slate to work with. All right, so the main gist of this about how conductors and potential work is this idea. Let's say that I've got a chunk of conductor. I'm just going to make it sort of an oblong. I suppose I was originally trying to draw a sphere, but it doesn't work. I don't draw as well with a mouse as I do with my hand, I guess so. But the idea is the following: if you ask yourself about if this conductor is in electrostatic equilibrium, which means that the charges are not moving around. So electrostatic equilibrium, there's in a conductor, you've got equal numbers of positive and negative charges inside this conductor. That's why it's electrically neutral. And what I'm going to say now is a little bit about how we can use Gauss's law to discuss how charges distribute themselves here. So let's say I have positive and negative. Let's say I have, this. It's electrically neutral. Let's say that I take a little eyedropper or something like that, and I drop a little dab of positive charge on here. Now, an electrical conductor, these charges are completely free to move around. So I dropped a little bit of positive charge, a little eyedropper, put it right on the surface. Okay. So what happens now? All right. Now, the thing about it is all the charges in this conductor, including these ones that have just been added to it, they are completely free to move. Completely 100% free to move. That's what a conductor is. An ideal conductor is one where these are free to move. And the thing about it is the presence of these charges right here momentarily at least produce an electric field in this region, and all the charges in the conductor will feel that electric field. So these charges, first of all, they want to be as far away from these other positive charges as they can get, so they dash and they spread themselves. Now, where they spread themselves is they keep moving, or how they spread themselves is they're going to keep moving around until the electric field inside of the conductor is zero. Okay? Eventually it's going to reach an equilibrium point where the charges are going to stop moving around. Okay? So what will happen is these charges will spread around, they'll move until the electric field inside the conductor is zero. If the electric field is not zero inside of this conductor, in the conducting material that this conductor is made out of, the charges inside of that conductor are going to feel an electric force, and they're going to continue moving. So they're going to keep moving until the charges have redistributed themselves in such a way so that the electric field on the inside of the conductor is canceled. So this will eventually turn into, I'm going to make this sort of odd line. It's supposed to be the same thing. Eventually it goes to this, where I've got positive charges as far away from one another as possible. And the electric field on the inside of this conductor is 0. We kind of use proof by contradiction here. If the electric field wasn't 0, the charges would continue moving until it is 0. And remember, the charges inside the conductor are completely free to move. So they keep moving around until the electric field gets canceled somehow. So that's the situation we have. Inside of a conductor, the electric field is 0. And that means that if I were to, and this is a little bit hard, I might have to zoom, but I guess I'll use a really thin thing here. I want you to imagine that I take a Gaussian surface that is just on the inside of this conductor. So that's supposed to be just on the inside. Barely on the inside, just a touch inside. Okay. If I take this Gaussian surface right here, remember it's in the meat of the conductor. If I was going to calculate what is E dot dA for every point on that surface, well, if the electric field is 0 at every one of those points, the electric flux must be 0. Because remember, Gauss's law says that the electric flux through a closed surface, which this is, that is supposed to be equal the charge enclosed. It's supposed to be enclosed over epsilon naught. Okay. If I evaluate E dot dA at all these points just within that are just on the inside of the conductor, we said at every one of those points E is equal to 0, and this integral on the left hand side is really easy to do. It's 0. But what does that tell you? That tells you that the charge enclosed must be 0. So remember that charge that we put on the conductor? Originally put a little eyedropper on there. The only place it can live is right on the surface, not inside. It doesn't live on the interior of this conductor anymore. It lives right on the surface. Okay, so that's sort of the starting point. The electric field on the inside of a conductor is 0. Now, what does that mean as far as voltage? All right, well, I'm going to remind ourselves what our voltage formula says. If I go between any 2 points, if I go from point A to point B, and I can pick wherever I want for those 2 points, the difference in voltage between those 2 points is the integral of E dot ds, where ds is some arbitrary path that goes between those 2 points, between A and B. So let's say I'm inside the conductor and I go from there to there. Okay? And if I want to know what's the difference in voltage between this spot A and this spot B, and I just say, well, I'm going to follow this path along there to get from point A to point B. Well, what's E along every point along there? It's 0. E, the electric field is 0 inside there. So no matter what ds I choose in going from point A to point B, as long as I have to be able to stay within I could choose whatever one I want, and this is very convenient because this stays inside the conductor, then that means the difference in voltage between point A and point B must be 0. In other words, they're at the same voltage. And I could pick any point A and any point B inside this conductor that I like. And what that says is, every point in this conductor, no matter which pair of points I choose, there's no difference in voltage between any of them. Which means that inside of this conductor, the voltage is constant. Okay? So the voltage is constant. So E equals 0 implies the voltage inside here is a constant. I'll just put const. There we go. So the electric field 0 means the voltage is constant on the inside of a conductor. Now, this implies that the surface of a conductor, on the surface here, is an equipotential surface. it is a surface along which the voltage is constant. And and we know from the lab that we did last week that you haven't turned in yet necessarily, that the electric field always points perpendicular to the equipotential surfaces. So the electric field on the outside of this conductor would point perpendicular to the surface of the conductor. So on the inside, the electric field is 0, but on the surface, the electric field points. That's supposed to be. That's pretty close. Points like that. This one point again. That's supposed to be perpendicular. If this is positive, they were pointing out. If it's negative, they'd be pointing in. But something like that. Well, they're all supposed to be perpendicular to the surface at each of the points. This one over here is, I don't know. I'm not going to draw that one, I guess, because it's too close. That one's there. That one kind of goes off that way. Oops, that one is a terrible one. Did not draw that one very well. Wonk. More like that. There we go. Something like that. All right. So does that make sense? And then there'd be other electric field vectors that would come out on this side, but I'm just not going to draw them because they're right close to the edge. And that's the main thing that I want you to know, is how the electric field and the voltage are related to one another. That if the electric field is 0, it doesn't mean that V is 0, it means that V is constant. It doesn't change. It could have a value. This could be 120 volts in here. It just means that this points at 120 volts and that points at 120 volts. And if that's true, if the voltage remains constant, then it means the electric field is 0. And you could see that also from our definition, or our other formula that Chase was asking about earlier, that the electric field, say in the x direction, is minus dV dx. What does this mean? If the voltage does not depend on x, then this derivative is constant, I get the electric field is 0. Same thing would be true for y. If I take the derivative of v with respect to y, I get the ey and get 0 there, meaning v doesn't depend on y, then the y component is 0. It doesn't mean that the voltage is 0. The voltage doesn't have to be 0, it just has to be constant or uniform, and that tells you that the electric field is 0. And that's basically what I wanted you to take away from lecture 3. The other things are just examples of how things work. If you want me to go into detail about how those individual things work, let me know. Just give me a comment here, and I'll talk about it. And the other thing I want to ask is, how are folks feeling as far as being comfortable doing the integrals? Did my integral setups, did those make sense? Were those okay? So I guess I got kind of two questions that I'm on. First of all, are some examples that you want me to go over in more detail with regard to the types of applications that I gave you, which is kind of extra information? If so, which ones? And what about the integration, the calculus method of finding voltage? Because we haven't talked about that too much here, like from point charges. So I'll pause and just let you tell me what you want to see. Yep. Good. Simon says the integrals make sense. Yeah, you could just put them in your calculator. Absolutely. I guess I'll make a comment about that as I wait for other questions to come in. That as far as the exams go, I think it made this clear, but I'll make it. I'll just reiterate it just to make sure that it's clear. When we do get to the exam next week, at least that's the plan so far. When we do get to the exam next week on on this electric stuff, if you have to do an integral, remember everything is it's open internet, open book, open note, it's open everything, open calculator, all that sort of stuff. You have everything at your disposal. I still want you to do your own work, so don't ask anybody to help you with it. Do your own stuff. but you're allowed to use the web there. I'm not going to use any lockdown browser, any nonsense like that to try to lock you out of the internet, because, I mean, the truth of the matter is, if I do use a lockdown browser on your computer to run the test, I think there's still a 100% chance that you'll have one of these sitting next to you anyway, right? So they can be easily circumvented, so I'm not even going to try. There's no reason for me to do it. I just trust you enough to do your own work on it. So I don't think a lockdown browser is going to solve many problems anyway. So I won't be doing that. I had a question about that in my last live stream from yesterday, from another class. 24.3. Yep, let's have it. Chase is asking on 24.3. I got the book right here. Let's have a look. Cole's got another question too about the integration technique, so I'll have a look at that as well. All right, so Chase's question on 24.3, I'll just read it here so folks have an idea what we're talking about. It says, we have absolutely charged plates are separated by 5.33 millimeters. A potential difference of 600 volts exists between the plates. What is the magnitude of the electric field between the plates? What is the magnitude of the force on the electron between the plates? And then how much work must be done on the electron to move it to the negative plate if it is initially positioned 2.9 millimeters from the positive plate? All right, so I'll give you some hints about how to do that one, because it's still out there. You can still complete it. So we're going to use, so let me erase here so we can, I can have a little bit more space to sort of, okay. All right, so in a lot of ways, this is similar to the problem that we talked about, at least part of the problem that we talked about. We've got this, these parallel plates, and we know from what we talked about earlier that these produce uniform electric fields. And I know that one of them is 600 volts higher in voltage than this one. Okay, I'm just saying, so I've got 0 volts and 600 volts here. So this one's 600 volts higher in potential than this one is. They don't have, it could be that, and remember that there's that KQ over R plus C sort of thing. This one could be at 20 volts and this one could be at 620 volts. The difference is 600 volts. You don't know which one is which. But the only thing that matters is what the difference is. So that's sort of the situation. And we also have that there's a distance here that is known that's 5.33 millimeters. Millimeters. Okay. And then it's saying, okay, you got that potential difference. What's the magnitude of the electric field between the plates? Okay, so you can use your definition, the delta V is equal to negative E dot ds, and you could sort of figure that the electric field is going to be uniform and that sort of stuff. You could also use that idea that, remember, E, X, or Y, if you wanted to put it in here, is like negative. Oh, that's a terrible D. Don't you hate it when your D's don't show up right? All right, erase, start over. Not completely over. But there we go, better. Okay, something like that. Now I know what the difference in voltage is, and I know what the difference in the position is between these two. Looks like we could calculate the electric field like that. Okay, so it says something like that. So that's part. Now it's giving you a hint about what part A looks like. The magnitude of the force on the electron between the plates. Well, now you're using the fact that once you know what the electric field is, and you know an electron has a certain amount of charge, what would be the force that it experiences there? So that sort of thing. So you can calculate that as well. How much work must be done on the electron to move it? Well, remember there's a relationship between the electric potential and the if a particular charge that you know is moving from point A to point B, and point A doesn't always have to necessarily be from 0 to 600 volts. It could be from anywhere in here to 600 volts, or from anywhere from here down to 0 volts, whichever way. The difference in potential gives you information about, if I have a particular charged particle, how much potential energy, how much is that potential energy changing going from point A to point B. It's what we talked about earlier on. And remember how the work is related to the change in the potential energy. So think about those things. So all those relationships are sort of in play. Okay. Hopefully that sort of answers the question. I am going to, in the interest of time here, I'm going to go ahead and start answering Cole's question about how to go step for step for the last example in the second slideshow. But if Chase wants to answer in the live chat whether he thinks that's adequate hints on that problem, let me know now, and I'll start on Cole's and then maybe bounce back to Chase's if it's not completely clear. So let me look, the second slideshow, last example, step by step. All right, so I got to go back to the other slideshow. Last example, the super fun one. Let's see if I can remember which the super fun one was. The super fun one was, oh yeah, where I did the disc, right? So could I go over that step by step? All right. I think I sort of can. Let's see if... All right, so I'm going to sort of set it up step by step, and my drawing, of course, is not going to be as good as we would hope, but we'll do our best. So here's the idea. It says we've got this disc. Okay, so it's a thin disc, and we want to know what the electric field is, or sorry, what the voltage is. Let me go back here. Voltage directly above the center of a uniformly charged disc of radius A. So right over the center, at this spot right here, what is V? Okay, and this is a whole disc, and it has a radius, so I'm going to put that in here. The radius of this thing is A, and it has a surface charge density sigma. There it is, bad. So that's our sort of start. I just saw Chase's question about the electric field. I would say instead of using V is equal to negative EX, I would say delta V is equal to negative E times delta X. Kind of just turn these D's into deltas there, and then you can probably use an algebraic formula rather than doing a derivative. It's, I think, more proper to say delta V is equal to E, negative E times delta X is a better way to put it. Okay, so comment on that if you need to, Chase, and I'll go into this one as well. So, so this is sort of the beginning that Cole is asking for. What can we do this step by step? So what we do, if you remember, what we did with electric fields with this is we said, well, let's choose a little piece of this. So that's a little chunk of area that is a particular distance away from the spot where I want to know what the voltage is. The thing is, I'm going to choose a particular shape for that, and this is where things get a little bit dicey, but not terrible. But I'm going to do this sort of as a top view. I'm going to say that little thing that's in there is this sort of weird truncated cone. Okay, so if I'm looking at that top down, this is supposed to be curved, this is curved, and this is directly out. So what I was showing there in the solution notes is that this actually sweeps out part of an angle. So this is supposed to be a little curve around there. And that arc length there has to do with the angle that's being swept out here between, if I don't know, this is hard to kind of draw, but if I say there happens to be where the center of the disc is, and that's my terrible drawing skills in paint. I'm doing my best. All right. So if the center of the, so I'm kind of coming out at an angle here, and then this is coming out at an angle there. So this angle right there, I'm going to call d theta. So there's an angle between these two lines. That's how much angle is being swept out here. Then this distance right here is, I'm going to call it, let me see, I want to make sure I use the same. I'm going to say that the distance from the center of the disk to this spot right here, I'm calling that distance r. Then this length right here is r d theta from the definition of the radian. So from here to here, so where the center of that is, I'm calling that r, and then the the distance of this little side right there is going to be r d theta. Then the distance from here to here, or looking down on it from above, from there to there along this edge, this is r and this is r plus dr. So we're just going to call that extra distance right there dr. So now this little wedge right here looks like a little, kind of like the smaller it gets, the closer it gets to looking like a little rectangle. So the differential area associated with that, oops, that should be an area. The differential area that we're trying to find how much charge is in there, because we're doing this so we can find dq. That would be equal to this side length multiplied times this side length. So when I do that, I've got r, and there's the dr from the other side, and there's the d theta from there. So this is the area size, and theta is, going to be got to be measured in radians. R is measured in meters or whatever. So that tells us that the differential amount of charge inside of this little bit, this little truncated wedge piece right there, is going to be the charge density times the area. The area is here. R dr d theta, whole thing. So that's how much charge there is here. Now, how far is that away? That's the question. So we usually say, well, we've got r, which is the distance from this arbitrarily chosen little piece up to there. How far is that? Well, I said the distance from the center to where this little piece is capital R. And I know this distance right here is what? What did I call that spot? What did I call it? I called it something. Z. Let's call that Z. Okay. I guess I didn't name it. I should have named it. I'm going to say that's like the Z, because we'll say the disk is lying in the XY plane, and then this is a distance Z above it measured along the Z axis. So I think that's what I wrote down there. Okay. So then R, if I look at this, this looks like simply like a right triangle. Of one side is length Z and the other side is length R. So this distance from here to here is simply the square root of Z squared plus capital R squared. Where R is not the radius of the disk, that's A. This capital R is the distance from the disk to that particular piece. And then I've got to add it up for all the different pieces. Some of them are at A, some of them are at R equals 0, and there's all these pieces that are in between. So those are the building blocks that we would use. So let me check my... Okay. So that's the building blocks that we would use then to build the integral. So then what I'll do is, let me clear out what's above. So I can show you how to build this integral. The voltage then that is produced by this little piece, I'm going to have to add the contribution due to all the pieces. So I have to have sum up, K times dq. So this, we're using kind of the point charge thing. It's kq over r. So it's, in this case though, because it's a little differential piece, it's going to be k dq over r, and this is the r we're going to use. So dq, that's going to go in the numerator here, is sigma times r times dr times d theta. Okay, and it's a double integral, but it's not terrible. And then I've got my little r now, the distance that every individual little piece is away from the spot where I want to know the voltage. I wrote that down below, and we'll just copy it up here. Something like that. And I'm integrating actually over all values of r and all values of theta. So I actually am doing a double integral here, which we talked briefly about back in the day when we were still meeting face to face. But here I'm going to say capital R, I've got to cover the entire disk. The whole disk needs to be covered. So in order to do that, I've got to integrate over R. I'm going to say all the possible values of R to cover all of the spots on the disk. It's going to go from 0 all the way out to a radius of A. That's supposed to be an A. Imagine it's an A. There we go. That's an A. And then I also have to integrate for all different possible angles that the little piece could be at. This one is at angle, theta is equal to 0, but I could have any old angle I want. I could be over here somewhere, and then the angle is pi, and I could be over here, and the angle is 3 pi over 2, and all that sort of stuff. So I got to have theta being all possible values from 0 all the way around to 2 pi. That's supposed to be a theta, so I'll try to draw a little bigger there. There we go. There's theta. And I just have to do this integral. So that's how I set up the integral. Notice that the theta integral is really simple. There's none of this integrand that actually depends on theta. So it's like if I'm integrating over theta, here's the first integral. It's like I could take this whole thing, which I'm about to put in parentheses, kind of in parentheses, like that, and I could say, well, that integral doesn't depend on theta. I could factor it out like you would do with any constant that's in an integral. I could factor it out I can't factor it out of both because it does depend on r yet. I can't factor it out of the r integral, but I can factor it out of the theta integral. And then this integral that's left over is just the integral of d theta, which you get 2 pi for. Because you evaluate that, d theta integrates out to theta, then you evaluate that at 0, 2 pi, it's 2 pi minus 0, you get 2 pi. And then you're left with this integral now only over r, and I have to perform this integral, which isn't terrible. This is actually, you could do a z substitution or something like that. You could, because you've got r d theta up here. You could, or not a z substitution, like a u substitution. You could say u is equal to z squared plus r squared. Z is a constant. R is my integration variable. The du is equal to 2r dr. Well, look at that. That's what shows up right there. So you could perform that integral without too much difficulty, probably using Calc 2 techniques that you've already learned in your Calc 2 class if you're in Calc 2 right now. So that sort of sets up the integral. Would you like me to go further? Because I think hopefully that explained where that part of it came from. And I'll pause now and see if there are any questions on how that setup happened. How that setup looks. Are there any questions on how I did that or where that came from? Okay. Do folks want any more explanation? Do you want me to go in once we get the answer for the voltage? Do you want me to show how we got that electric field expression? Go ahead and say so if you do want to see that. I'm pausing now just to see if you got. Did anyone want to see how we calculate the electric field from once we get the voltage from that integral? You can say yes or no, but don't stay silent because otherwise I won't know if you want to see it or not. In either case, I'll clear this out while I'm waiting. Okay, so Chase said he'd like to see the how the electric field is calculated. Okay, so when we do this integral here, when we perform that integral, we end up getting the following expression. We get that the voltage we get out of this, I'm going to just drop the plus c part. It ends up being 2 pi times k the electrostatic constant, times sigma, times the square root, I'm going to put this in brackets, times the square root of a squared plus z squared, and then minus z. So that's the voltage that we get. Now, if you want to find the z component of the electric field, remember what, if you have the voltage function, you could just say, well, that's equal to the derivative of the voltage expression, which we have right here, with respect to z. Okay. So, the next step would be just to perform that derivative here. Now, it's not terrible, but what we see when we perform, I mean, it's not terrible, but it's not just trivial either. So I'm going to try to write it out down here, and then we're going to see what we get. All right, so equals. All right, I'm going to just drop that because there probably won't be enough space here. We got 2 pi. These are all constants, so I can just not worry about those to start. Okay. Now, the first term is the hard one. This is, when I look at this is a squared plus z squared to the 1/2, and I have to take the derivative of that with respect to z. So a squared plus z squared to the 1/2 with the square root. So you got to do the chain rule on that. So the first thing you do is you go, okay, well I've got the power of the whole thing is 1/2. Okay, there's the half. Okay, and then I reduce the power of a squared plus z squared by 1. That means it goes from positive 1/2 to negative 1/2. Okay, so that's the same thing as the square root in the denominator. So a squared plus z squared square root in the denominator. Okay, so there's the first part. Now I have I have to multiply that times the, from the chain rule, I got to multiply that times the derivative of the inside. Now remember, a is a constant. We're taking the derivative with respect to z. So I get a factor of 2z. And there's one thing I forgot here, which I want to fix, is that the electric field, there's a minus sign there that I need to make sure that I have. A minus. Okay. Alright, so there's the first term. So minus 2 pi k sigma times this complicated thing. And the 2's cancel out, which is kind of nice. Okay, now the second term, really easy. Take the derivative of that with respect to z. Done. Alright. So there we go. That's the electric field, the z component of the electric field for that particular expression. Okay. So here's the dealio now, once you get here. So this is the general expression. We could cancel the 2's here if we like. It's not that big a deal, but I'll just do it just so we have it. So we have the z over the square root of a squared plus z squared. And now I ask, okay, in that second part, even further on, it says, what does your answer reduce to? What happens, in other words, if you allow the radius of the charge distribution to grow to be infinite? Remember, the radius of the charge distribution is a. So think about what that does. If a gets arbitrarily large and z is just some distance away from it, notice what happens. This term goes to 0 as a gets bigger and bigger and bigger and bigger. So as the radius of my disk gets arbitrarily large, it becomes an infinite sheet, doesn't it? And this first term going to 0 means the only term that's left is this constant term inside the brackets, which is just -1. The electric field then, the limit for for a going to infinity of that is that this goes to, with the minus here, it becomes just positive 2 pi k sigma, which, if you're careful, remember that k, the electrostatic constant, if I put it in terms of epsilon naught, which is our alternative way of writing down what k is, it's 1 over 4 pi epsilon naught. Notice what that is. If I substitute that in, what does this become? This is sigma over 2 epsilon naught if I plug that in there. It's the same thing. I'm just replacing K in terms of rating it in terms of epsilon naught. And that is exactly the expression we got when we used Gauss's law to calculate the electric field of a single sheet of charge that had a charge density sigma. And that was kind of the result I wanted to show you. This is an alternative way to calculate the electric field of an infinite sheet. The value of it is, doing this, you also get the voltage. And then you use it to calculate the electric field. This is the general electric field for a circular disk of charge, a circular sheet, a distance z above the center. And then as the disk gets really, really big, it basically reduces to, it looks like an infinite sheet. The electric field looks like an infinite sheet. Okay. Is that good? Are there any other questions on that? I'll pause to see if there are. Or if you have other questions that are not related to this particular problem. And while I'm waiting for these questions to come up, I'm going to kind of put what we're talking about this week, in context. So what we've done now today and this week is we have used the idea of the electric field to calculate the work and use that work expression to develop a new way of thinking about how electricity can be characterized. We can characterize it not in terms of necessarily the electric field. We can characterize it in terms of the voltage that it produces. And every spot in space then now has a voltage associated with it that is due to whatever charges are around. Okay, so this is a new way of thinking about what electricity does. Here, what we're doing here is we're saying electric charges produce voltages in space, which at every point in space, there's a number assigned to the electric influence that all those charges have. The difference between that and the electric field is here, the number that's associated with that is a scalar number. It's not a vector. I don't have to give the direction. The dependence, how the voltage changes from one point to the next, is enough to give you information about what the direction of the electric field would be through this relationship here. That electric field is related to the derivative of the voltage. The voltage is what we call a scalar field. It is a field, it is a function that depends on space, permeates space, but there's a number, just a single number assigned to it, every point in space. Now, what we're eventually going to be talking about, this is very theoretical in a sense, but what use this is that eventually we're going to be able to assign that to points in space within a circuit. So these voltages, I want you to understand the voltages so that we can talk about these voltages in the context of more practical problems starting late next week when we start talking about circuits and charge flow and currents and more practical applications of that sort of stuff. But this is the foundation of it. It's energy and work and electric forces and all that sort of stuff and how we can use that to express the influence that electric charges have in the region around them. Okay, so Chase has a new question. It's back to 24.3. Can you also go over parts B and C for that one? Let me look at that. I'm seeing. So I think we did talk about it a little bit, but I'll reiterate if it wasn't clear. So parts B and C of 24.3. So part B says, what is the magnitude of the force on an electron between the plates? Okay, and my hint for that one was, if you calculated the electric field for part A, remember that there's a relationship among the electric force, the electric field, and the charge that is experiencing that electric field. So take that into account. If you calculated E in part A and you know the charge on the electron, that one you should be able to look up if you want, then you know what the force is like. Remember though, remember the sign of the charge as well. So Part C, hopefully that's enough to kind of give you a hint on that. Part C says how much work must be done with the electron to move it to the negative plate if it is initially positioned 2.90 millimeters from the positive plate. The way to think about that one is, remember that there is a relationship between the difference in voltage between 2 points and the amount of change in potential energy there is, electrical potential energy between those 2 points. Remember, delta V is equal to delta U over Q. Once you know how much the potential energy changes, you can figure out how much work was done, because remember, the work done in going from point A to point B is equal to minus the change in potential energy. So there's a two-step process there. Use the difference in voltage and the charge on the electron to figure out how much the potential energy changed by, and then use how much the potential energy changed by to figure out how much work was done. So I think that's being pretty explicit, but if it's not clear, I'm sure you'll let me know. Okay, other questions? And here I'm just going to pause because my voice is getting hoarse. All right, well, no more questions from Sammy, she says. All right, well, I'll wait another 30 seconds just to make sure that to make sure there are no further questions, but, oh, Cole's got one. Okay, for part C, I used the work formula from Physics 1 and got the same answers. Yeah, I'd expect that you could totally do that. You could calculate the electric force and use that along with the displacement to calculate the work done. 100% exactly kosher to do that, no problem. Yes, Chase, there will be a review live stream. I'll post what time. I'm expecting that we're going to be looking at a live stream review next Tuesday rather than having our Thursday date. The reason is if we want to have that exam on starting Wednesday, I want to have the review before that, because I sure don't want to have a review while people have the exam out there and available and stuff like that. So I'm kind of counting on that right now, but I'll let you know if there's difference. So I'm going to be posting the lecture notes on Monday. The review lecture notes, that'll be the only lecture notes that I post until maybe later in the week when we would start other things. But once the exam gets posted, I'll have the lecture notes for the second half of the week go out as well. Okay, but yes, there will be a review live stream, no doubt on that. And I'll make the schedule 100% clear. I'll use announcements usually for that. Other questions or concerns? All right. Well, if not, then I'm hoping this was useful to you. If you do have comments about how we can improve this setup, please feel free to leave those in the discussion boards. And I don't see, it looks like some folks are signing off. But I'll look forward to seeing you sometime early next week. I'm planning on Tuesday. We'll have the lecture notes. We'll be up Monday morning at 8 a.m. and then we'll have the review live stream probably about this time, same time on Tuesday. That is my plan. But I do have some other things that we're going to be scheduling. This is not related to our particular class, but I do have other things that are on my schedule that I have to make sure that our live streams do. But my priority is to make sure that you have your live stream review for your exam in a timely fashion. So thanks again for your attention. Hope this was useful. The live stream, the recording will be up here in just a couple minutes after I get done here. You can review it there at your leisure if you need to. But thanks again, and we'll see you next time.